Hi, we are Subgroup 7 from STK2973 Analytical Technique under Dr. Junida. In this video, we will explain our answer in Assignment 2. There are 4 members in our group, which are Nurul Ashura binti Ahmad Azahari, Rachel Tan Huiru, Tan Singro, and also Yo Sing Yi.
First, let me explain task 1. Consider the following chromatogram for a mixture of analyte A and B. Recommend which column is more efficient for chromatographic separation for component B. Give your recommendations on the number of theoretical plates N. For task 1, the column efficiency for component B was evaluated using the number of theoretical plates. The theoretical plate number was calculated by using the equation N equals to 16 times Tr over W power 2, where Tr is the retention time and W is the peak width at the base. Based on the calculation shown on the slide, column 1 gives a significantly higher number of theoretical plates compared to column 2. Column 1 gives a theoretical plate number of approximately 1.11 times 10 power 3, while column 2 gives a much lower value of about 3.31 times 10 power 2. This indicates that column 1 is more efficient, as a higher theoretical plate number corresponds to narrower peak and better separation efficiency for the same retention time. Therefore, column 1 is recommended as the more efficient column for the chromatographic separation for component B.
Hello, my name is Ashura. So today I will present task 1 of assignment 2 for STK2973. In this task, I will compare column 1 and column 2 using the chromatography performance parameters such as number of theoretical plates, height equivalent to the theoretical plate, and the peak resolution. And finally, I will make the recommendation on which column give a better separation and efficiency. Given the information, 2 analytes were separated, which are component A and component B. Their retention time and peak width are followed, as the retention time of A is 8 minutes and retention time of B is 10 minutes. Peak width at best, column 1 with A 1 minute, with B 1.2 minutes. Otherwise, column B2 with A 2.3 minutes, with B 2.2 minutes. Also, both columns have a length of 25 centimeters. So, the first one, we need to calculate the efficiency. So, I use this formula. N equal to 16 in the bracket, Tr over width, close the bracket, and the square root of 2. So this is the formula of number of theoretical plates present of N. So we calculate for column 1, component A and component B, and then for N for component A, I got 1024. For component B, I got 1110. So this we can show column 1 has the higher plate number, meaning it's more efficient. And we go to column 2, we use the same formula. For component A, I got N equal to 194. For component B, I got 331. So as we know, the column 2 has much lower plate number, meaning it is a less efficiency. Okay, second part is I need to calculate the plate height. So I use the formula H equal to L over N, where L equal to 25 centimeter and N is calculated above. For column 1, plate A, so I use the formula. I got H equal to 0.0244 centimeter. Meanwhile, for B, I got 0.0225 centimeter. As we know, the column 1 has a lower H value, so it be better efficiency and narrower peak. For column 2, I use the same formula. For A, I got 0.129 cm, and for B, I got 0.0755 cm. As we know, the column 2 has a higher hash value, meaning poorer efficiency. Let's go to part 3. Part 3, I calculate the peak resolution, which is R capital S. So resolution formula, I use the RS equal to 2 in the bracket TRB minus TRA, close the bracket, over WA plus WB. So the retention time difference, I use the formula TRB minus the TRA. So 10 minus at equal to 2 minutes. For column 1, I use the formula, the retention formula. RS equals to 1.82 for column 1. Meanwhile, the column 2, 0.89. So the interpretation of this resolution interpretation, RS more than 1.5 is baseline resolution accepted. Meanwhile, the RS is less than 1 is poor separation. So the column 1 has a baseline separation, which is RS equal to 1.82. Meanwhile, column 2 show the poor separation because RS equal to 0.89, which is less than 1. Based on the result I calculate, the column 1 has a higher theoretical plate, lower plate height, better resolution, and baseline separated is accepted, while column 2 give a lower red plate. Meanwhile, column 2 give a lower plate number, higher plate height, poor peak resolution. Therefore, I recommend column 1 for separating analyte A and B because it provides a better efficiency and separation performance. That is my end of my task 1 presentation. Thank you.
For task 2, the question wants us to predict the elution order of the compound 1, 2, and 3 based on the chromatogram below and explain our answer. Molecule 1 is methoxybenzene, molecule 2 is benzene, and molecule 3 is nitrobenzene. This is our answer and explanation. In the chromatogram, the leftmost side is the molecule that elute first, and at the rightmost side is the molecule that elute the last. Our answer is 3, 1, and 2. Our explanation is reverse phase HPLC consists of non-polar stationary phase and an aqueous polar mobile phase. The retention time for non-polar molecules is longer than polar molecules, which allow more polar molecules to elute more readily and easily. This chromatography operates on hydrophobic interaction. The C18MS column is non-polar and very hydrophobic. Nitrobenzene is the most polar molecules and least hydrophobic, thus is the first to be elute, and followed by methoxybenzene. Benzene is the last to be elute as it is non-polar and the most hydrophobic.
Lastly, let me explain to you our answer in task 3. So in task 3, we need to identify the functional group in the following FTIR spectrum for the given two chemical structure and interpret our result for the answer. So this is the first FTIR spectrum given. By referring to the FTIR absorption frequency table in the slide given, we are able to identify all the functional group in the following FTIR spectra for the given chemical structure. There are 3 main bands that we can identify in the chemical structure. So I have highlighted in orange in the table given in the picture. The strong band at 1660 per cm has confirmed the presence of carbon-carbon double bond in this molecular structure, while the band at 3023 per cm has indicated the existence of hydrogen atoms directly attached to the carbon that has a carbon-carbon double bond. Lastly, the multiple band within the range between 2850 to 2960 per cm and also 1350 to 1470 per cm has confirmed the presence of long-chain hydrocarbon. This SEIR spectra is confirmed the chemical structure of cis-triooctene. Next, the second diagram has shown the FTIR spectra for another chemical structure. So in this slide, the picture show another FTIR absorption frequency table. So from what I have highlighted in the picture, we can notice that all of the spectra that we notice in the spectrum is mostly come from amide. Another thing that we should take note that is that amide have a same NH stretching band that similar to amine, primary amine, that it has two bands between 3500 to 3100 per cm. This spectrum is corresponding to the primary amide compound spectra, and it also allows us to make confirmation of the chemical compound given containing amide group and alkyl chain. Overall, the spectrum given allows us to make confirmation of chemical structure for the both given compound. Both FTIR spectra strongly support the assigned chemical structure through characteristic and diagnosed peak. The spectral features are consistent with the literature FTIR reference value. And this is our explanation for assignment 2 from task 1 to task 3. Thanks for watching.